Give me about 30 more seconds and I'll begin. All right, pardon me, I had to eat a quick snack, and I figured everybody didn't want to listen to me chewing. All right, so as a reminder, we completed 1.1 and 1.2 last class, which means they're due next class, which would be the 28th by midnight. The 1.3 and 1.4 homeworks, I still need to edit. That was weird. I still need to edit some. Unfortunately, I need to learn to edit my assignments before I make them visible, because once a student goes into them, I can't actually edit the homeworks anymore. I can make questions non-necessary, but I can't put new questions in. I can't actually physically remove the questions. It shows it there, and it shows you as having a grade for it, which is not exactly what I'm going for. So I'm going to try and make sure I don't do that again in the future. But with these two, it's just a little weirder. There's a lot of homework problems in 1.3 that I'm not really worried about. In fact, most of 1.3 is kind of arbitrary. But we need 1.3 as an introduction to 1.4 and pretty much everything else about the first couple chapters of this course. So what exactly am I going on about? Well, let's get into that. So 1.3, and let me make sure I have lots and lots of space so I don't do what I did last time. That should be more than enough, 6 pages. So 1.3, the average rate of change. The average rate of change. So a rate of change is something that we've already talked about. Rate or ratio means fraction. Change, unless you're getting into like percentages, this is generally a difference. So the word rate of change is a fraction of differences. Remember slope? Slope is a rate of change because it is a fraction of differences. And that formula, as a reminder, is m equals y2 minus y1 over x2 minus x1. You are calculus students. You never, ever, 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 ever get to forget that formula. If you forgot it, learn it now, learn it yesterday, learn it a week ago. You never get to forget it. Things with slope, things with equations of lines, you never get to forget it. It's not allowed. It will be a problem for now and the rest of your lives if you forget it. I can guarantee that. So, excuse me. Slope, that letter M, which I wrote a little sloppy, but that's an M on the left, is a y2 minus y1 over x2 minus x1. Let me do this. And why is that blue all of a sudden? I don't know. Now you don't want to give me color options? Technology, am I right? Okay. Just keeping this in the first quadrant to make things as easy as possible. Let's say we have our first point here, and we have our second point here. So P1, P2. Now each of these points has coordinates. P1 is x1 comma y1, and then P2 is x2 comma, that looks like a semicolon. Come on, thank you, comma y2. So if this is 0.1, then on the x-axis, that has to be x1. And if this is 0.2 on the x-axis, this has to be x2. On the y-axis, very similarly, this height would have to be y1, and this height would have to be y2, because that's how coordinate pairs work. They tell you how far left, right, up, or down you go. The first one being the left or right, the second one being the up or down. And then we could connect those points with a line. And the steepness of that this distance right there, that's the horizontal distance known as the run. And then this vertical distance is known as the rise. And the run and the rise are literally those differences of x2 minus x1. That looks like a y. And then this one's y2 minus y1. So the slope is just the ratio of those two lengths. So that's the slope of a line. But we want to get into start talking about the slopes of curves, and to introduce that idea, because lines have a constant slope, it means it never changes. So the steepness at this point is the same as the steepness at this point is the same as the steepness at this point. The slopes at any point, the slope at any point on a line is always the same. If the slope here is 2, the slope here is 2, the slope here is 2, the slope here is 2. So that's algebra. We're calculus students. So now we're going to get into curves. Once again, I don't know why it keeps changing me to blue, but it is what it is. So curves bend. They could do something like this. And it probably goes on to the left as well, but it doesn't have to if it's a real life function. So let's say, once again, why am I in blue? It says it's blue, but it's black. I'm extremely confused. It's never done that to me. So let's take, I don't know, this point right here. Let's call this P1. And let's call this P2. Now, what I'm going to make is a secant line out of those. So I'm going to make a little secant line. And I do actually want the secant line to be blue. And that's not going to be a good steepness. So this is what we call a secant line. A secant line goes through 2 points on a curve. You have a point here and a point here, you connect them. Or I could do it here and connect them. That would be a secant line using that and that. Or I could have a secant line here and I could connect those, but I only want to see one at a time. So every curve has literally millions and trillions of possible secant lines that you can make out of it. It's about why you want to do a particular secant line. Now, slope is a measure of steepness. Now, once again, this line has a constant steepness. It's always the same steepness or grade or slope or rate of change, no matter what you want to call that. They are all the same thing. This curve is bending. It's going up and then it's coming down and then it kind of flattens out and then it goes back up and it could be doing a bunch of different things after that. So curves bend, which means the slope here is different than the slope here, is different than the slope here, is different than the slope here. The slope is different at every single point. Now, there may be some points where like the slope here might be the same as the slope here. There might be some coincidences, but the slopes can all be different numbers. They don't have to match, they don't have to be the same. So to start off calculus, what we do is we say, all right, well, let's find the slope between 2 points on the curve, and we'll call that a secant line, and the slope of that line the slope of a secant line is the average slope of all points between P1 and P2. Now, that might seem like a lot to grasp your head around. Maybe just take it with a leap of faith. But in other words, so the slope at this singular point, if you want to talk about the slope of a singular point on a line, you have to use what's called a tangent line. Tangent means touch and go. So like here at P2, let me do it in red. P2, because the curve is kind of going this direction, the secant line is basically just you drawing a line parallel to it at that singular point. So this is a tangent line at P2. This would be a tangent line at P1. And you can see those lines have a drastically different slope. P1 has a positive slope, P2 has a negative slope. That's the biggest difference between them. Now, what I'm saying is if you measured the slope at the infinitely many points between P1 and P2, if you then added up all those slopes and divided by however many you actually used, that value would be the same as the slope you calculate from P1 to P2. The slope of a secant line is the average slopes of all points between them. So that's a good starting point for getting into calculus, which is trying to find the slopes at these singular points, to find the slopes of these tangent lines instead of using secant lines. So the slope of a secant line, this is what we call our average rate of change. So the average rate of change from P1 to P2 with coordinates x1 comma y1, it's going to take me too long to use subnotation, and x2 comma y2, but you all should know that it has the little subnotation like up here. It should look just like those. So the average rate of change from P1 to P2 is literally the definition of slope. It's y2 minus y1 over x2 minus x1. But it's better to use function notation. So function notation, instead of y1 and y2, you have f of x1 and f of x2. So y1 is f of x1, and y2 is f of x2. So our average rate of change, and this is the formula I stick with, AROC, average rate of change from point 1 to point 2, is f of x2 minus f of x1 over x2 minus x1. This is literally the formula for slope. This was something that was done in pre-calc 1 as well. This is a formula you have to have memorized. So this calculates the average slope from one point to a second point. That's what this will do for us. It doesn't tell us the slope at the first point. It doesn't tell us the slope at the second point. It does actually tell us the slope of at least one point in between. There's a theorem for that we don't need to worry about too much in here, but it's kind of cool that it does say at least one point has that slope. But again, this is just the slope of a secant line. So let's try out an example. And that's in blue. Give me black. Yeah, so usually that color shows what I have picked. It's probably because Word crashed earlier. So we're going to, for this example, find the average rate of change of the function f of x equals x squared from x equals 3 to x equals 6. And this is going to be example 1a. For example 1b, we're going to use the same function, but we're going to do it from different x values. So we're going to find the average rate of change for the function x squared, our very, very basic introductory parabola, from x values of 3 to 6. Now you need completed points to do this. All I gave you was the x values, but you can find y values by plugging them in. So the first thing you have to do is plug in to find the y values. And I'm putting that in quotes because we're going to call them function values, f of x2 and f of x1. So f of 3, that would be 3 squared, which is 9. That is our y2 or f of x, I'm sorry, y1 or f of x1. Because 3, we're going to call that the x1, 6, we'll call that the x2. So when we plug in 3, we get a 9. That's the function value. That's the output. Similarly, if we do f of 6, we'll get 6 squared, which is 36. That is our second output. That's what we call f of x2. That's f of 6. x1 is the 3, x2 is the 6. You can see the numbers you plug in that associate with them. That's one of the advantages of function notation we talked about last time. So now the numbers that we need are the 3, the 6, the 9, and the 36. All we're doing is calculating a slope using that. That is literally what an average rate of change is. So why does it keep going back to blue? Our average rate of change, that's f of 6 minus f of 3 divided by 6 minus 3. y2 minus y1 over x2 minus x1 literally means the same thing. But the f of 6 was the 36. The f of 3 was the 9. So we got 36 minus 9 in the top. In the bottom, that's just the 6 minus the 3. 36 minus 9 being 27. 6 minus 3 is 3. And 27 divided by 3 is 9. So that is the average slope from x equals 3 to 6. If you do any different x values, that is likely to be a different average slope. That is averaging the infinitely many individual slopes at singular points that we don't even know how to calculate at this point. It's unfathomable at this point to us, but not for long, thankfully. But if you were to calculate that infinitely many slopes and then average them out, it would average out to 9. Let's try another one. For B, for B, let's go from x equals 0 to 3. Now, you don't have to call the 0x1 and the 3x2. You can call the 3x1 and the 0x2. Just make sure that your function values are labeled accordingly as well. If you call the 3 the x1, then when you plug that in and get 9, then the 9 is the f of x1 this time. So again, it might be a good idea to label them. I'm calling the x1, that's the x2. So f of 0, that's the f of x1. That's 0 squared, which is coincidentally 0. That's our f of x1. F of 3 we've literally already done. That's 3 squared, which is 9. So that's our f of x2. See, last time I called that f of x1, this time it's f of x2, because last time the 3 was the first point, this time it's the second point. So our average rate of change, that's f of 3 minus f of 0 over 3 minus 0 So again, the numbers we're plugging in are the 9, the 0, 3, and the 0. So the f of 3 was the 9. Whatever, I'm not changing the color again. The f of 0 was 0. Then the bottom was just 3 minus 0. We already have those numbers. 9 minus 0 is 9, 3 minus 0 is 3, and 9 divided by 3 is 3. It has a much smaller slope. Now, let's, for fun, actually after we do this, for fun, let's do one more C. Maybe a little less work on C. But let's go from x equals -3 to x equals +3. So f of -3 is -3 in parentheses squared, which is +9, not -9. F of +3 we already know is 3 squared, which is 9. So our average rate of change, the f of 3 minus f of -3 over 3 minus -3, that's 9 minus 9 over 3 plus 3, which is 0 over 6, which is 0. Huh. So the average slope between those two values is 0. You might think that that doesn't make sense, but we haven't visualized it yet, so maybe that would help. So let's graph this. I'm just going to do it by hand really, really quickly. All these points are in the top portion of the graph, so I'm not going to do too much on the negative portion. We have the point 3, 9. We have the point 0, 0. So here's 3, and let's have a height of 9 be about here. You can see I'm stretching the x-axis a little more than the y-axis. And then we had a point at 6 about here, which had a height of 36, which is probably way up here. And then our curve would look something like this. Pretty standard parabola. Ignore my mediocre artistic ability with this tablet. And then the left side looks very similar. In fact, we did the calculation for the -3. It had a height of 9. If you did the calculation at -6, it would also have a height of 36. So there's our line. So in blue, I'm going to do the first one. We went from 3 to 6, correct? Yes, from 3 to 6. So in blue, this will be the first secant line connecting. That doesn't look great. This point and this point. So this would be the secant line for A. And that slope is 9. Now in red, I'll do B, which was going from 0 to 3. So if you connect these 2 points, you can see that we still have a positive slope. This is B's secant line, but it is definitely smaller. It's not as steep. It came over the slope of 3. So we can see that the secant line going from 3 to 6 is a larger number. We can see visually it's steeper. Larger number, steeper. Smaller number, less steep. Now let's do from -3 to 3, and let's do that with a, about dark green. So again, here is that point, here is that point. So if we connect them, it's a horizontal line. And guess what? Horizontal lines have a slope of 0. You were supposed to know that fact inside and out. So again, those lines, those secant lines, are a great visual representation of the average slope, because when you see that line, you can see, hey, that line C, it's flat, so it should have an average slope of 0. Even though the infinitely many points from -3 to 3, this is a negative slope, this is probably like a negative, -6. It would be exactly -6 at -3. Don't ask why I know that. We'll find out later. And then it would be something like a -2.5, and then a -2, then a -1, and then a 0. The slope here is 0. This tangent line would be completely horizontal, which you can barely see that, but it would be 0. Again, I said tangent, not secant there. It's the only one I'm going to describe. And then we end up like a slope of +1, +2, +6, and then over here at 6, that would be 12. So if you averaged all those slopes from 12 to 6 between those, you end up getting 9. In fact, the average of 12 and 6 is 9, but that's just a coincidence. And that's because quadratics have cool features like that. So this is something we did in pre-calculus. This is nothing new. This is nothing new. So what do we do in calculus? What we want to do in calculus is find a way to talk about the slopes at a single point. Instead of using 2 points, we want to talk about the slope at 1 point. So in calculus, what we do is we want to merge the 2 points from an average rate of change formula into 1 point. We do this by saying the second x value is an arbitrary constant, which we label as h, added to the first value. So in other words, when I talk about the x value 6 in comparison to the x value 3, 6 is 3 plus 3. So I could say that h is 3. It's a coincidence. If I wanted to talk about 7 in comparison to 3, then the h would be 4. If I wanted to talk about the value of 3.5, that would be an h value of 0.5. It's just the difference between the two numbers. The 2 points. Let me delete my second the. So in calculus, we want to merge the 2 points. We want to take them and squish them together. We want to take the second one and just kind of slowly make it closer and closer and closer in theory. The idea of taking a number and making it closer and closer and closer to something. That sounds familiar if you watched the last class's lectures, which I know everyone has. This idea is the same as a limit. We want to get smaller and smaller and smaller to merge these points. So that idea, like where we had a function and we plugged in 0.9, then 0.99, then 0.999 to take a limit, the idea here is to make the h something like a 1, then a 0.1, then a 0.01, then a 0.001. And then you just see what the number is getting closer and closer and closer to. Okay. So instead of using x2, we call x2 x1 plus h. And again, those are supposed to be little 2's and little 1's. This makes the average rate of change formula change into this thing. Color. So our average rate of change becomes f of x1 plus h, because that's f of x2, minus f of x1, over, now x2 is x1 plus h, and then minus the x1. I'm going to scroll up real quick to show you the comparison here. The two things that I'm highlighting, these used to say x2. See right here, f of x2 and then x2. But we just said we're going to make x2 the first one plus that arbitrary h. So h is just a small number. It doesn't have to be small. It can be 1,000 or 1,000,000, but because we're trying to merge the points, the idea is we want it to be small. But arbitrary because it could be 1, 0.1, 0.01, 0.05. It doesn't have to be 0.01 or 0.0001 or anything like that. But check this out. x1 in the bottom minus x1 in the bottom, those two things are going to cancel each other out. And what this thing turns into, this is getting frustrating, is f of x1 plus h minus f of x1. The top does not change, but the bottom does. The bottom is just an h. This right here is known as, and again, this was seen in calculus, the difference quotient. But we don't have to use the little sub ones. So the final way I'll write this is f of x plus h, then minus f of x, all divided by h. I'm going to box this one up because this is the best format. Why? Because when you use x, you're implying that you can plug in any number that you want. So by doing that, it gives me the original version, but also it means I don't have to plug in an x. I can actually get formulas for this thing based on any x value, not just a specific one. So what I'd like to do is use this and go back to the x squared function and create an example with these h values. Now, I will admit, this is not a typical sequence that I'm going to have us doing in this class. This is going to be, I'll do it once, you'll see some in the homework, and then I'm probably never going to do it again because it is extremely time consuming. It's more of a numerical methods approach, and it's just to get us an idea of how things work. Okay, so example, what do we have to 2? Yes, example 2. So for the function f of x equals x squared, once again, find the average rate of change for an x value of x equals, most of those were centered around 3, so let's stay close to the 3. And then with h's, for a, we'll do 1, which is honestly too big. For b, we'll do 0.1, and for c, we'll do 0.01. So we are actually going to be plugging in numbers for h. This is something you'll never see me do again in this class. What values are we plugging in? 1, 0.1, and 0.01 as separate problems. And I'm going to need some space, so let me scroll out. Let's put a right here. So again, our x value is 3, and our h is equal to 1. So our average rate of change is f of 3 plus 1 minus f of 3 all over, and it's just h. Remember, the bottom is not x2 minus x1 because we did that little quick substitution and it changed the bottom's format. And this is really, really popular. You're going to see this. You need to memorize this now and for the rest of the semester because it's going to be a common theme in chapter 2. So the bottom is just the h, which we said is 1. Well, 3 plus 1 is 4, so that's f of 4 minus f of 3 over 1. I'm not going to show the plugging in. 4 squared is 16. 3 squared is 9. We've already done that. So that's 16 minus 9 over 1. 16 minus 9 is 7. So that's 7 over 1, which is 7. What we have just done is found the average rate of change between x equals 3 and 4. That is seen literally right here because when you plug in the 3 plus 1, the x plus the h, it's 4. This is not a new type of problem. If you go back and do the average rate of change from 3 to 4 in the previous example, you would be doing 16 minus 9 over 4 minus 3, which is 7 over 1, which is still 7. Okay, so that's the slope of the tangent, sorry, I said it right the first time. That's the slope of the secant line going from 3 to 4. Now let's start at 3, but let's have it a lot closer. We're going to have the h be 0.1, which means we're going from 3 to 3.1. So our average rate of change, AROC, is f of 3 plus 0.1 minus f of 3 all over just the h, which is 0.1. So that's f of 3.1 minus f of 3 divided by 0.1. We'll pull out a calculator to make this easy. 3.1 squared is 9.61. So that's 9.61 minus 9 divided by 0.1. I need to continue this down here. 9.61 minus 9 is 0.61, so that's 0.61 divided by 0.1. Now, you should not need a calculator to do this. You are calculus students. You should know how to do decimal divisions. This is the same thing as if you move each decimal right once, 6.1 divided by 1, which is 6.1. So that says the slope of a secant line from 3 to 3.1, very close together, is 6.1. C. Let's go from 3. So again, this was going from 3 to 3.1. Now let's go from 3 to 3.01. So this is 3, adding 0.01 to that would be 3.01. So these 2 points are really close together. In terms of graphing, you're going to have a hard time doing that by hand. Give me about 15 seconds. I need to drink some water. All right. So our average rate of change would be f of 3 plus that very small 0.01 minus f of 3 all over 0.01, which is f of 3.01 minus f of 3 divided by 0.01. So let's square 3.01. 3.01 times 3.01. And you get 9.0601. 9.0601. 90601. Minus 3 squared is 9 still. Then divide that by 0.01. Subtracting the top gives you 0.0601 divided by 0.01. Dang it. I was talking. Sorry about that. When I had that last cough, I forgot to take my mute button off. All right. So was the last thing I said this 6.01? Was the last thing you heard me talking about when we boxed up the 6.01? Okay, cool. So I will now say out loud what I was saying again. I apologize for that. Surprisingly, that's the first time that has happened in a whole semester. Well, I guess half a semester since we started this in March. Okay, so thank you for catching me on that. So what I was saying was, when we had an h value of 1, the slope between going from 3 to 4 was 7. Then we went from 3 to 3.1, and it was 6.1. Then from 3 to 3.01, it was 6.01. So as we make this h smaller and smaller, we're getting closer and closer to a value of 6. So we say, what does the average rate of change seem to be approaching if we keep making this h smaller, like a 0.00001? It would probably be like 6.00001. It seems to be going towards 6. So what that is suggesting is that if we want to take those 2 points, x1 and x2, and merge them together, let's just take the limit as this h goes to 0. We want to squish them together, which means the h goes to nothing. The x1 becomes the x2. So we say, maybe we should take the limit of this difference quotient as h goes to 0. Now, what this gives us is our instantaneous rate of change that I did not spell correctly. It's instant with an A. Capital A. So this will give us what we'll call an instantaneous rate of change at a single point. This right here is the first step of calculus. By throwing a limit on the difference quotient, we are now doing calculus. The difference quotient is something that you did in pre-calculus. The limit is something that we said, all right, this is the first step of calculus. Taking limits is our first step. But this is really the first step because the study of calculus is all about change. And this gives us our first idea of real change at a singular point instead of multiple points. We can come up with the slope at 6. So for example 2, example 3, I used to call it example 2 in my old notes. It's now example 3. Let's find the instantaneous rate of change of the function f of x equals x squared at x equals 3. So what we want to do is take the limit as h goes to 0 of that difference quotient formula. So of the difference quotient. This gives us an instantaneous rate of change. So that's the limit as h goes to 0 for f of, now we said our difference quotient was this formula, f of x plus the h minus f of x over h, where our x is going to be 3 and the h we're going to leave as h. All over h. And I wrote an x here. I meant to write a 3 there. Let me just undo that. Bad habit. I will also point out this is another case of we usually don't do things this way. We're usually not going to plug the number into the definition, which is this. We are generally not going to plug the number in here. In the next section, you'll see what we generally do. This is kind of a one-time only thing. But let's just see what happens at 3 specifically. So we don't plug in the h because we're going to make it go to 0. So we don't want to go through that 0.1, 0.01, 0.001 nonsense. But we do want to know what happens specifically at x equals 3, so we're plugging that in. So f of 3 plus h, this would be the limit as h goes to 0 of 3 plus h squared minus, when we plug in 3 to the function, that's 9. We already know that. F of 3 is 9. That's because we're just squaring the input. And then over h. Now, if you try and plug the 0 in right now, it's going to make the bottom 0. If you plug it in here, 3 plus 0 is 3, 3 squared is 9, 9 minus 9 is 0. You get 0 over 0, which is indeterminate. You have to wait to plug it in. How do you know how long to wait? Generally, you'll see something massive cancel. Generally, the h in the bottom needs to go away. So this is the limit. As h approaches 0, let's simplify the top. The 3 plus h, we can FOIL that out. So that's 3 plus h times 3 plus h, then minus the 9 all over the h, equals, and yes, you have to keep writing the limit as h goes to 0 until you plug it in. We're going to FOIL the 3 plus h. 3 times 3 is 9. 3 times h, that's a plus 3h. The inner is the same thing, h times 3, that's another plus 3h. And then the h times h is a plus h squared. We have the minus 9 at the end. I'm just going to put a little really thin parentheses around this. You don't need it. I'm just trying to emphasize that that was this. The minus 9 at the end is just still the minus 9 at the end. And the bottom is still an h. Now again, those parentheses are not really there. That was just for visual flair. Look what happens. The 9 and the minus 9 cancel. This 9 and this minus 9 cancel. Gone. Gone. The 3h and the 3h will stack to a 6h. So this is now the limit as h goes to 0 of 6h plus h squared all over h. And if you plug in the 0 now, it's still not going to work. The top and bottom are both 0. But what we can do now is, in the top, there's a GCF. This is a very common issue. So let's factor it out. So that's the limit as h goes to 0. Take an h away from the 6 and the h squared. What are you left with? Taking it from the 6h, you're left with 6 plus h squared had 2 of them. Now it's only got 1 of them when you take 1 away. And at the bottom, you've got an h. Well, with an h in the top factored and an h in the bottom factored, they cancel. So this is now the limit as h goes to 0 of just 6 plus h. And if you plug in 0 into this, you won't get that indeterminate form. In fact, there's no more denominator. So now we can plug in. So this becomes 6 plus 0. Oops, it didn't change the color that time. Which 6 plus 0 is 6. Now before, we thought that it was approaching 6. It went with a mediocrely large h, it was 7, then 6.1, 6.01, the next would have been 6.001. So this confirms that. If you somehow manage to plug in 0.00000000000 with 10 billion quintillion infinitely many zeros, you'd get 6. So that says the slope at x equals 3 is 6. At the singular point, you no longer need 2 points. It's not an average slope. It is the slope at that singular point. Now, the slope at that point would be different than at 0. It would be different at 12. It would be different at -3. It would be different at +6. And you think, wow, I'd have to go back and count and do this math every single time just to do it at a different number. And in fact, you don't. Which is why I said earlier, this is not the way to do things generally. There is a much simpler and a much quicker way to do this. And the way that is instead of plugging the number in, you leave these as x's, you'll get a formula in the end to then plug the 3 in or the 6 in or the -12 in or whatever number you want to. And then you can find slopes at different points as quick as snapping your finger 10 times or 9 times or however many times I just did it. So again, this works, but it's a pain in the butt if you have to do this for multiple x values. So not my suggestion. but it leads us into how we're really going to approach things. Okay, so that's about 50 minutes in. Pretty good timing. That is 1.3. So 1.4. Differentiation using limits of difference quotients. Differentiation is exactly what we just did, arguably. Differentiation kind of sounds like difference quotient, differentiation, difference. They're similar. So differentiation relates to the difference quotient. So that's why we say doing differentiation using limits of difference quotients. There's another word for differentiation. Derivative. Why did I spell with an I? That was silly. Differentiation is the process of finding a, and I want to have this all caps. Excuse me, is the process of finding a derivative, which is the instantaneous rate of change at any x value, not a specific x value, at any x value. So there's a lot of words that all mean the same thing: instantaneous rate of change, derivative, differentiation, limits of different quotients. All these mean the same thing: tomato, tomato. Is it synonyms? Pseudonyms? I was thinking homonyms at first, but that's not right. That's when they sound similar. Pseudonyms. So the derivative of a function, f of x, is the instantaneous rate of change at any x, and has the notation f prime of x. Kind of looks like a exponent that's a colon. I usually don't have it so bendy. Usually just looks like that. Kind of looks like an exponent of 1 on the f. That is what we call prime notation. That is called prime notation. So that is read as f prime, or the derivative of f of x. F prime means the derivative of f of x. All of these things relate to slope. At a singular point. Instantaneous rate of change is a slope at a singular point, as we already said. I'm just saying the same things over and over to make sure that we really get the idea. So what does this look like? F prime of x, the derivative at a specific x value, is equal to the limit as h goes to 0 of the difference quotient, which was f of x plus h minus f of x, all divided by h. This is the limit definition of the derivative. Derivatives are slope. Instantaneous rate of change is slope. F prime of x is slope. This all relates to how a function is changing. Calculus is the study of change. Unless you're a dentist and then it's the study of the gunk between your teeth. But for us, calculus is the study of change. So again, we just do the difference quotient. We take the limit as h goes to 0, and bam, we will get a formula. And that formula will describe the slope at any point. So we don't have to do the difference quotient for an x value of 3, then at an x value of 6, then an x value of 9. You don't have to do all that crazy math we did last time. You just do it once. And then at the end, you get a formula to plug your numbers in that will be much, 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 much simpler. Like me, I knew this answer was 6 because of that simple formula. It makes things a lot easier. Now, we will go back and do the x squared problem again, but let's do a simpler one to start this out. Example 1. And we are going to, let's do it here. Find the derivative derivative of the given function. Find the derivative of the given function. For a, we're going to have f of x be 2x minus 6. So this is our function. Now this function is a line. Lines have constant slope. And in fact, if you remember your algebra, which you better, we'll remind us of those equations of lines once again in a few examples, but the number in front of the x, if it's solved for y, which f of x acts like y, this is the slope. So you should all know instantly that the slope of this line is 2. And because it's a line, the slope is 2 everywhere. But now let's use calculus to prove that. So we are doing calculus. So f prime of x. This will be the limit as h goes to 0 of f of x plus h minus f of x all over h. So we're plugging the x plus h into the x. So x plus h is what's going to go where you originally saw an x. If you need to do that to the side, you certainly can, and that's the way I do it in pre-calculus, but I show everything in one instance in calculus. But you are always more than welcome to do some stuff to the side. So this will be, I need my, and I'll do colors. So f of, not yet. I almost want to close this and open another one and see if it's going to be silly still. So this is 2 times the x plus h. It also makes me just want to do everything in blue. Minus 6. This right here, all I have right now, just this, that's f of x plus h. So instead of 2 times x, it's 2 times x plus h. And then there's a minus 6. So all this that I have circled, and the circle is going to go in a second, that's the f of x plus h. So then we have our minus. And this is supposed to be the f of x. F of x. So minus f of x. Now f of x is 2x minus 6. I'm going to write this incorrectly at first. This is wrong, this is wrong, this is wrong, this is wrong. And then you go over. So just temporarily highlighting. This highlighting was the f of x plus h. This highlighting is the f of x. Why is this wrong? Why in the world is this wrong? Because I have the minus and then I wrote the f of x. Well, this minus is supposed to go to the whole function. This is a very, 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 very common issue. Almost every time you need to wrap that f of x in parentheses. This is very common. If your function has more than one term, if you want to subtract it, you got to wrap it in parentheses. You were supposed to have mastered that in arithmetic and algebra classes. And then the bottom was just supposed to be our regular old h. Remember, we're not plugging anything in for h. We're leaving h alone until the very, very end, then we make it a 0. If you try and plug it in now, I guarantee you, you'll get 0 over 0, which is indeterminate. All right, so this is equal to, let's keep going, distribute the 2. So that's the limit as h approaches 0. 2x plus 2h minus 6. Distribute the negative, so that's a minus 2x plus 6. Watch your signs, all divided by h. Well, there's some stuff that can cancel. This is very, very, very common. 2x minus 2x, gone. Negative 6 plus 6, gone. With polynomial functions, you should get a decent amount of cancellation. In fact, any term that doesn't have an h ends up canceling. Spoiler alerts for polynomials, not necessarily radicals or rationals. Those are different issues. Okay, so equals. What are we left with in the top? Just the 2h. So that's the limit as h goes to 0 of 2h divided by h. Well, look at that. You have h's on top of each other, so they cancel. Gone, gone. So that's the limit as h goes to 0 of 2. Now, if you plug in 0 here, you're going to get a perfectly fine form. You cannot have h's in the denominator. Otherwise, you're going to end up indeterminate. I can guarantee that. You are looking for this cancellation. Once you see this cancellation, that's when you know you can plug it in for polynomials. And usually for others as well, but there's exceptions to every rule. So where do I plug the 0 in? I don't see an h. Well, if this said 2x and I asked you to plug in x equals 5, you wouldn't. You would just leave it as 2. If there's no variable, you don't plug anything in. So the answer is just 2. You can't plug it in this time. This is kind of a simple case. Usually you can plug it in. And you'll see that in the next one. Don't worry. So at the very beginning of this problem, I told you I know slopes 2. I know it for several reasons. First reason I know is because this is an equation of a line, and the number in front of the x is supposed to be the slope as long as it's solved for f of x or y. So look, that matches with what we got. I also know some slightly more advanced calculus, and I can just look at that and know the answer in other ways, but we're going to teach you that. Don't worry. There are quicker ways to find this answer for more complex polynomials, thankfully. But we got to do it the hard way before we do it the easy way. B, f of x equals x squared. Now, I'm not saying at x equals 3 this time. I'm just saying in general. So when we're done with this, we'll get a formula. And if I wanted to know specifically what the slope is at 3, I could then plug 3 into the formula. And then I could find out what happens at 0 and 6 and negative 12 and whatever x value I want without having to do this painful algebra every time. You'll only have to do it once. So we're supposed to find the derivative of this, which means we're finding this guy, f prime of x, which the definition of the derivative is this limit thing, the limit as h goes to 0, and it's f of x plus h minus f of x all over h. Again, we are using this formula right here. I'm even going to highlight it. Don't you dare ever forget this formula. You won't be using it constantly throughout the semester, but it will come back and bite you every now and then. All right. So the limit as h goes to 0 of f of x plus h. So the function is x squared. So this should be x plus h squared. Then minus the f of x, which is just the x squared. That's always given to us. The minus part's always given to us. It's the f of x plus h that you'll have to do some jazz with. And then all divided by h. Again, this was originally just a slope formula that we have made more complicated because we want our 2 points to become 1. All right, well, this parentheses squared, that's the limit as h goes to 0 of x plus h times x plus h, then minus the x squared, leaving that part alone, all over the h. So this is the limit as h goes to 0. We're going to FOIL out that parentheses, pair of parentheses, x plus h times x plus h, and you're going to see this multiple times in this class. You should have seen it in pre-calc multiple times as well. That's x times x is x squared, plus the outer x times h is xh, or hx, the order doesn't matter. The inner is the h times x, so again, it can be xh or hx. The x or the h can be first, it doesn't matter, but be consistent. I went xh, so I'm going to go xh again. Again, the outer and the inner match. This is pretty common to see for binomial squares. Then the last is the h times the h, which is h squared. So again, these four terms right here, we're just foiling out the parentheses. Then we have the minus x squared that was already there. Then we have the all over h. Do not be lazy and skip writing the limit. Do not be lazy and skip writing the over h. When you're lazy, you end up forgetting them later and missing them and getting things wrong. I can guarantee it. Been there, done that, bought the t-shirt. These get really ugly for a hot second, but the good thing is lots of things will cancel. The x squared and the minus x squared are gone. The xh and the xh add to 2xh, adding the same thing. Apple plus apple is 2 apples. So xh plus xh is 2xh. So this is the limit as h goes to 0 of 2xh plus h squared, all divided by h. Again, after combining like terms and canceling. Now, just like in this previous problem, when we had a GCF in the top, h, we need to factor that out and cancel it to get rid of the h in the bottom. Same thing happens here. There's an h and an h, so we can factor it out and cancel. So here's the GCF again of h. So this is the limit. As h approaches 0, take the h out of the top terms. What are you left with? From the first one, the 2 and the x are still there, plus from the second term, it had 2, so there's 1 left over. Then this is all over h. And we have now hit the point we've been waiting for. There's an h as a factor in the top and h as a factor in the bottom. They cancel. So we get the limit as h goes to 0 of just 2x plus h. This is your signal. This is your flare. When the h's are gone out of the bottom in general, that's when you can go and plug the 0 in. If you plugged it in at any point before now, you'd get 0 divided by 0. Don't believe me? Try it even at the last one. This would be 0 plus this would be 0 divided by this would be 0, which is 0 divided by 0. Indeterminate. Nobody knows what it is. But now we can plug it in. So that's 2x plus plugging the 0 in. Just gives us 2x. So the better way to write this, instead of just writing the 2x, use the notation. The derivative of the function, in other words, the function that guides its slope, that dictates its slope no matter what x value, is 2 times x. That is the formula for the slope at any point of the function. That is amazing. I don't think a lot of people really understand how amazing that is. We are able to calculate the slope at a singular point, not 2, at a singular point without having to take the h going from 1 to 0.1 to 0.01 to 0.001 without that big process, just some, not the simplest algebra in the world, but stuff you should know. And we get a relatively simple formula to plug in an x value. So if you want to know what the slope is at x equals 3, plug in 3 here. Guess what 2 times 3 is? It's 6. So I'm going to make a little memo of that. At x equals 3, f prime of 3, so that's saying the slope at 3 is 2 times 3, which is 6. And that agrees. with what we got before when we did the limiting process with the h's getting closer and closer to 0. We deduced that we were getting near 6. Then by doing very similar algebra, but by plugging the 3 in first, we were able to see that the slope is 6. But if you do this problem the original way, and I now ask you, all right, well, what's the slope at 6? What's the slope at 7? What's the slope at 9? You'd have to do all of this work again. Whereas the way we just did it, all you do is plug in 6 or 7 or 9 here. So the slope at 7 is 2 times 7, which is 14. The slope at 9 would be 2 times 9, which is 18. The slope at 0, 2 times 0 is 0. I can fire these off in like a half a second each. The slope at 1, 2 times 1 is 2. The slope at 17, 2 times 17 is 34. These formulas are amazing because very often in the real world, we want to study change. These things called marginals in economics, if you will, not margarine, marginals. When we talk about like the speed of a car, that's change. It's change in position. When we want to talk about acceleration, that's change of speed. These are all derivatives. These are all fascinating concepts. So derivatives, rates of change at a singular point. What is happening right now? Hey, this virus that's going around, how is it changing? Because we might only want to look at a singular day because yesterday doesn't matter anymore necessarily. I want to make another memo here that when we got to, from the previous example, the limit as h goes to 0 of 2xh, didn't need that there, plus h squared all divided by h. I want to show you an alternate way. The way I've done this 2 times in a row is I took a GCF out of the top and then canceled. Your calculus students, if you know a shortcut here, please feel free to use it. You can cancel a factor while it's written in a non-factored version as long as it's everywhere. So because that h is in this term, and this term, and this term, it's in every single term, top and bottom, you can cancel it. If it's missing from one of them, you can't. So I'm going to just pretend for a hot second. If this h was not here, I could not cancel the h squared and the h. I could not cancel a factor there. I could not do that because the h isn't everywhere. But typically what you'll see is that it is. So I can say, all right, get rid of this h, get rid of this h squared and make it an h to the first because there were 2 and now there's 1. Get rid of this h. And now what we have is the limit as h goes to 0 of 2x plus h. The bottom's gone, so I don't need to write it. This h squared is now an h to the first. And you literally get the same answer. I do not care which way you're doing this when you show your work. I care that you have a method that works for you every single time. So again, also just as kind of extra work, if you wanted to know, all right, well, what's the slope at 0? Well, that's 2 times 0. You're using the 2x, not the original function. That's 0. So the slope at 0 is 0. What's the slope at 10? At x equals 10. What is it currently changing? How is it currently changing? Well, that's 2 times 10, which is 20. This gives us expected values in the near future. So if you know what's happening at 10, you can easily predict what will happen at 11. Whether or not that's accurate, if we're talking real world information, it doesn't have to be accurate, it can be close, but at least we'll have a close estimate. And that's something that, again, these people are doing when they model virus, the population of how many have it, how many have died, how many will get it. There's a lot of calculus involved with that stuff. All right, so let's do another example like this, because again, this is much more common, at least for now. Black. Example 2. Oh no, I'm sorry, this shouldn't be example 2. This is example C, 1C. This is just C. Pardon my mistake. So again, we're going to find the function that will dictate the slope of the function. That's our goal here. We're finding f prime of x for a function. Now let's do the cubic function, the basic cubic. Now, we are eventually going to learn a way to do this without the limits. It's a bigger shortcut, and I can tell you the answer right now is 3x squared based on that process. If I had x to the 4th, it would be 4x cubed. If I had x to the 10th, it would be 10x to the 9th. I can do those in less than a second. But before we get to that, we need to practice with the more methodical version of this because it is important. It's important to understand the complicated version before we become masters of the simple version. So we're doing the limit. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. And you should have that formula written down in front of you. So f of x plus h, now we're cubing it. Cubing, not squaring, that's a 3. And we're plugging x plus h in this time. So this is our f of x plus h. Then minus, the f of x is just the x cubed, that's always given. And then all over the h. Or we can't plug in the h equals 0 until that h in the bottom's gone. So this would be the limit as h goes to 0 of x plus h times x plus h times x plus h, then a minus x cubed all over h. Now that's going to get super tedious to show, so let's just do that one to the side. I will do this one to the side. The point of this problem is, this is going to be even more tedious than the last one with the foiling because we'll have to foil and then we'll have to do something else. If I do an x to the 4th, that's one more layer of complexity. An x to the 5th, that's another layer of complexity. Every exponent higher makes this problem one step longer, in fact. Point being, if I ask you what the derivative of x to the 100th is, you don't want to do that this way. You will hate your life because you would have a parentheses raised to the 100th power, so you'd be doing x plus h times x plus h times x plus h times x plus h times x plus h, and there would be 100 of those things. And I would cry if I had to do that. So our goal ultimately is to get out of this, but for now, let's make sure we understand how it works by keep stepping it up in terms of complexity. So let's do some side work, and let's do all the side work in green. Okay, so side work. Let's just focus on the x plus h times x plus h times x plus h. Well, the first two we've already done. X plus h times x plus h was right here. It was x squared plus 2xh, the xh and the xh combined to make a 2xh, plus an h squared. So again, x squared plus 2xh plus h squared. That's this. That's the first pair of parentheses. The last one, I'll do in red now. So again, I have multiplied out the first two all in green. I just scratched the heck out of myself, ow. But I have not multiplied the last one. There is no special name for this product. Foiling is just a binomial times a binomial. That's how we got this. There's no special name for a trinomial times a binomial. You just have to distribute everything to everything. So distribute the x and the h to the first parentheses. Or you can distribute the x squared, the 2xh, and the h squared to the second parentheses. Distributions work either way. So taking the x, that was weird. Why did those just move? Okay, apparently I can switch that around. So in blue, I'll show these three products. So the x times the x squared is x cubed. That's the first in each parentheses. Then the 2xh times the x, that's a plus 2x squared h. Again, that was the second term or the middle term times the red x. Then the h squared times the x would be a plus x h squared. In, let's go with gray, we'll do the h. So the h times all three of those. So that's plus h times x squared is x squared h. I'm just always writing the x's first for consistency. Then the h times the middle term, h times 2xh is a plus 2x squared h. Then the h times the h squared at the end is a plus h cubed. So let's see. X cubed doesn't have a like term, so that's x cubed. So the first one I'm done with. I'm gonna cross them out as I use them because there's a lot going on. 2x squared h does have a like term. 2x squared h is like x squared h. They have the same variable factors. Now there's an imaginary implied 1 there. So you're adding 2 and 1 to get 3. So that's a plus 3x squared h. So I did those with squiggles. Then we have an xh squared and a 2x squared. Did I write something wrong somewhere? 2x squared, xh squared. I did something wrong, didn't I? The h times the 2xh should have been 2xh squared. This 2 right here I have wrong. I'm going to give you a second. Put that 2 over the h. I think I said it right. I may not have. I just put my exponent in the wrong spot. So I need to erase that. Sorry about that. Terrible looking too. There we go. So in the blue, there should be an x squared h term and an x h squared. In the gray, there's an x squared h and an x h squared. That's correct now. So those two are like terms. So this x h squared and this 2x squared make a 3x h squared. And then the h cubed is not like anything. So this right here is what's going to be plugged in to the 3 parentheses being multiplied. I'm going to erase that in just a second. But that was the side work. So we can go back to the limit now. So back to the limit. We have the limit, so equals the limit as h goes to 0. So the parentheses times itself, that's the light green ink. X cubed plus 3x squared h plus 3x h squared plus h cubed, then all divided by h. Right? Question mark? No. This is a common mistake that people make. What am I missing? And this is where in class I'd wait for someone to say, you forgot the f of x. The black ink I have right here in the top is just the f of x plus h. So I can't forget the minus f of x, which was the minus x cubed. I can't forget this part right here. I see a lot of people miss that. And then I'll see some people stop here and they're still wrong because they don't have the over h. Okay, a lot of ugly work so far, but all for a cause, because guess what? The x cubes cancel on the top. There are only terms with an h in the top now, which is generally what we want to see. So now we have equals the limit as h goes to 0, 3x squared h plus 3x h squared plus h cubed, all divided by h. If you want, you can just cancel out all the individual h's, or you can take a GCF out. I usually ask who prefers what in class, but I can't ask that right now to every single person and wait 10 minutes for text responses. Since I've done the GCF multiple times, I'll do just the crossed out version this time. So there's an h here. There's an h squared here, so that's now an h to the first. There was an h cubed, so that's now an h squared. And this h is gone. I got rid of an h from every single term because every single term had it. If one of the terms didn't have it, I couldn't do it. See, I can't cancel the h's here because there are terms without it. But there are no terms like that here, so I can cancel them, which gives us our limit. Sorry about the color, but I'm not changing it now. Of h, as h goes to 0, of 3x squared plus 3xh plus h squared. Now, we can plug in the 0. So this is the limit. I'm sorry. When you plug in the limit, we no longer write limit, obviously. It's just the 3x squared plus 3x times 0 plus 0 squared. Oops. Which is 3x squared. The middle term is now plus 0. The third term is plus 0, which is 3x squared. So the derivative of our function, in other words, the function that dictates its slope at any x value, is 3x squared. And if you remember, I said that at the very beginning of the problem. I did it in half a second. It's an amazing tool I have at my disposal. There will be problems, at least one, probably two on your first test and on the final, probably only one on the final, where you have to do this. That shortcut I know that I'm able to, oh, it's 3x squared, or if it's x fourth, it's 4x cubed. The fact that I can do that in a quarter of a second, if I give you a problem that says do this by the definition, you have to do this limit stuff. You have to show your work, or you would receive no credit. Now, most derivatives that I ask you about going forward after this section, you get to use this short and simple formulas. And they're not always short and simple, but they're always simpler than the limit version. You have to be able to do things both ways. We will do the limit version much less, but it is still mandatory. You still absolutely have to do that. $12.30, okay. Now, if I wanted to know the slope at, say, 0, 3 times 0 squared is 0. If I want to know the slope at 1, 3 times 1 squared, that's 3 times 1, which is 3. If I want to know the slope at 10, 10 squared is 100, 3 times 100 is 300. Wow, that slope got really large really fast. That's because cubic functions grow really, really fast. They grow faster than quadratic functions. Every larger exponent you have makes the function grow faster and faster. All right. As a reminder, lines. Point slope form is y minus y1 equals m times x minus x1. I gave this to you last class. And slope intercept form, let me just put that a little lower, is y equals mx plus b. If my Algebra 1 students can handle equations of lines, my calculus students better be able to as well. Why do we need to handle equations of lines? Because what we're very often interested in is, let's go back up to some pictures earlier. So these are all secant lines. And we drew up these secant lines. And you could find those equations by using those 2 points and the slope. But what we're going to be more interested in is finding the slope of a tangent line where we just have that single point and the slope that they give us. So there's a little green dotted line right here. What's the equation of that line? Or if we put that dotted line here, what would the equation of that line be? So let me redraw this, that stuff up, but with tangent lines instead of secant lines. So we are often interested in the graph and or equation of the tangent line to the curve at a single point. So to get the line, we got to know how to put things in point slope form and get slope intercept form out of it. So here's our basic parabola. Here's our x squared graph. Here is a tangent line at x equals 0. Here's a tangent line, if we call this x value 3. There's a tangent line. That is terribly written. I will do that again. At x equals 3. Maybe over here, this is -6. Here's our very steep tangent line at x equals -6. So again, very often we're interested in tangent lines to points on curves. The reason being, if we're talking about a small amount of time that's going to go on, just like a day or something, those lines can be used to predict what's about to happen. Will they be perfect? No. Are they a quick way of assessing what is close by? Yes. So again, tangent lines are often used for approximating a function value as long as we're close to where the tangent line is. So if I want to know what happens at 3.1, I could use the tangent value to get a good approximation. But I wouldn't want to use a tangent line at x equals 3 to predict what happens at x equals 20, because those are going to be very, very far removed. The quadratic graph would be very, very far away from that line by the time we make it to 20. It's okay at x equals 4. It's great at 3.1. It's kind of trash by the time you hit 2 units away for x squared. And that depends on the function that you're dealing with. Some functions, a tangent line is better for a longer amount of time. This gets into what we call numerical methods, where we start having computers do a lot of things for us. And your TI-83 actually does a lot of these types of calculations for function approximations. So I'm going to do these in a different order. Sorry, give me a second. More like 15 seconds, actually. Okay. Let's scroll. We are in example 2 now. Color. Find the equation. I could have typed that. Of the tangent line to the curve at the specific x value. So for A, we're going to have f of x be x squared. And let's do this at x equals 3. Now, we're not going to reinvent the wheel. From before, we know f prime of x is equal to 2x. I'm not going to do that limit definition for the derivative again, for the same one we've already done. Our function's x squared, we know the derivative. Again, this is the function that dictates the slope. Now, to find an equation of a line, you need 2 things. You need a point and you need a slope. So we need a point and a slope to make a line. The point, you just plug in x equals 3 to f of x. the slope, you plug in 3, x equals 3, into f prime of x. You're going to plug the 3 into the function to find its y value. Then you plug the 3 into the derivative to find its slope. And yes, we already know that, but it's super short, so I'll show you the work. So f of 3, that's 3 squared, which is 9. So our point is 3 comma 9. That's our x1 and our y1. Now we plug the 3 into the derivative, which that function's 2 times 3, which is 6. That's our slope at the x value of 3. So at 3 comma 9, at that point, the slope is 6. It only has to be 6 at that singular point. So we have our slope, we have our point. This is our x1, our y1, and our m. So we just plug them into the point slope form. Y minus y1 equals m times x minus x1. Don't plug anything into x, don't plug anything to y. Just the x1, the y1, and the m. So again, I'll write that one last time, like so. So we get y minus, the y1 was 9, equals the m, which is 6, parentheses, then x minus the x value, which was 3. Then we take this and solve it for y to get it in y equals, which is slope-intercept form, and that's the best form of a line, most people would argue. So that's y minus 9 equals 6x minus 18, distributing that, adding 9 to both sides. Will give us y equals 6x minus 9. Oops, that's a 9. That is the tangent line at x equals 3. So if you graphed it, if this right here is 3 comma 9, oops, that was terrible. I hate this tablet. I know hate's a strong word, but I really don't like it. There's our tangent line, y equals 6x minus 9. So it touches at x equals 3 and x equals 3 only, necessarily. All right, we got about 10, 15 minutes. Let's do another one. That was example 2A. Let's do B. I am getting sick of that, so I'm just going to leave it in blue and red. Let's do f of x equals x cubed at x is equal to 1. So we need to plug that value into the function and its derivative. Now from before, we know f prime of x is 3x squared. We did that earlier, not going to reinvent the wheel. So f of 1, this will find the output, that's 1 cubed, which is 1. So our point is 1 comma 1. The x and the y values are symmetric, just there. The slope is f prime of 1, which is 3 times 1 squared, which is 3 times 1, which is 3. That's our m. So our tangent line is y minus y1, which is 1, equals m, which is 3, times x minus x1, which is also 1. Distribute the 3, you get y minus 1 equals 3x minus 3. Add 1 to both sides, you get y equals 3x minus 2. Watch your signed arithmetic. Your calculus students, you should know your signed arithmetic. I'm going to skip drawing this one. Feel free to do it on your own. C. Now, I will admit this one's going to be drastically more work. I'm actually thinking if we have enough time for that. I think we can. So f of x is equal to 1 over x. And let's do this at an x value 4. We don't know the derivative of this function yet. We never found it. So we have to do that whole limiting process for this one. So first, find f prime of x. This is a significantly longer problem for multiple reasons. So f prime of x is the limit as h goes to 0. I'll write the definition one last time of f of x plus h minus f of x all over h. So that would be the limit as h goes to 0. Now f of x plus h, this x is in the bottom, so it's 1 over, and the x turns into an x plus h. This right here is the f of x plus h. Then the minus, f of x is the original function, 1 over x. Then the bottom of the main fraction is h. This is what we call a compound, or some people would call it a complex fraction, because it's a fraction inside of a fraction. It's inception. We don't like that. We don't like that. We can't have that. We need to clean this up. To do that, what we have to do is find an LCD and then there's multiple methods for this. You can find the LCD of all the fractions and multiply that out, or you can do it a slightly different way of the top. So I'm only looking at the tops. I'm ignoring this h in the bottom since it's not a fraction. So just the x plus h and the x. Well, that LCD is x times x plus h. They're completely different. So you have to have them as a product. And then we will multiply each fraction, top and bottom, by what it's missing. So multiply top and bottom. FedEx is here. Multiply, and now my dogs are gonna start going nuts, sorry. Multiply top and bottom by what's missing. This guy and this guy. We're leaving the h alone. So equals the limit as h goes to 0. I am leaving the h alone in the bottom. The 1 over x plus h needs to multiply top and bottom by h. That's the missing factor from the LCD. That's how we get LCDs. That's the more normalized way of doing things. LCD is the product of everything, x plus h and h. So that was the first one. Then for the second one, minus, here's our 1 over x. So it has the x, but not the x plus h. And I did these as h's. I got distracted by everything going on. Those are supposed to be x's. The LCD was this thing, x times x plus h. So they're supposed to be x's. X, x. Sorry about that. The second fraction has the x in the bottom, but not the x plus h. So we multiply top and bottom by x plus h. I'm also going to do something extra. The h in the bottom, I'm going to write it over 1. That way, we have something special in a minute or two. So equals the limit as h goes to 0. This first fraction is now x over x times x plus h. Hold on for a second. Minus the second fraction, the x plus h times 1 is x plus h in the top. The bottom is the LCD, x times x plus h. Then all over h over 1. Now, in the top portion of the fraction, I'm just looking here. These now have a common denominator, so we can combine them. So we're going to combine the top fractions, f's fractions. So this is equal to the limit as h goes to 0. Now, that's a minus and multiple terms, so you got to have parentheses. X minus parentheses x plus h all over its common denominator of x times x plus h. See, that's the same, so we only need to write the denominator once now that I'm combining the fractions. Then all over the h over 1. Distribute. So that's x minus h all over x times x plus h, then all over h over 1. The x minus the x is going to cancel. So on the top, we have just a negative h. So this is the limit as h goes to 0 of negative h over x times x plus h. Then that's all over h over 1. Note, a over b over c over d is the same thing as a over b division symbol c over d, which is the same thing as a over b times d over c. I'm going to use that to fix this. So it's no longer fraction divided by fraction. So now, this is the limit as h goes to 0 of negative h over x times x plus h. We're almost there. Times 1 over h. Again, the h over 1, we were dividing by h over 1. That's the same as multiplying by 1 over h. We're only able to do this once it's a fraction divided by another fraction. With all these pluses and minuses, we couldn't have done that before. With the separated fractions, we couldn't have done that before. So we still have that h in the bottom. We said generally that's what we want to see cancel. Well, now there's an h in just the top, there's an h in just the bottom. They cancel. So what we get is the limit as h goes to 0 of negative 1, don't forget the negative, that's a common mistake, over x times x plus h. Now you might say, Mr. Beckner, there's still an h in the bottom, but it's not just an h. It's an x plus h, and that makes a difference. Now let h be 0. So we get equals, no more limit, negative 1 over x times x plus 0, which is negative 1 over x times x, which is negative 1 over x squared. So the derivative, finally, is negative 1 over x squared. If this was a calculus class, we'd be doing a lot more like this and even more complicated. If this was a regular calculus class, this is an applied calculus class, so that's about as difficult as I go. I want you to ignore any that have a square root in the homework for now. For now, using the limit process, ignore square roots for now. It uses a technique that I don't really think we need in an applied business calculus class. So this is about as nasty as it gets using limits for now. This was a more complicated process, but you've seen it in the notes, which means you could see it in the homework, which means you could see it on a test. You might not. You might, or you might not. I said might a lot there, didn't I? That was weird. It's weird how I said you might more than I didn't. I wonder what that means. Okay. So anything you've seen here is good testing material. Like I said, the homework sometimes gets a little more complicated. I don't test on the more complicated stuff. I leave it there in the homework so you can see it, so you can try it. But the tests I keep more similar to the notes, just so you know. We're not done. All we've done is found the derivative. The whole point of this problem was to find a tangent line at x equals 4. So we've only done the first bit, but thankfully that was the worst of it. Now that we have our derivative, we can go and find the point, the slope, and jam that information into our equation, which we can finish in the time we have left. So again, f of x was 1 over x. F prime of x was the 1 over x squared. And we were supposed to do this at x equals 4. So to find our point, we do f of 4, which is 1 over 4. So the point is 4 comma 1/4. This is the reciprocal function, so the input is just flipped to get the output. F prime of 4, this will give us our slope at that point. That's negative 1 over 4 squared, which is negative 1 over 16, so that's our m. The only information we need now is those two numbers in this number, the point and the slope. And we put those numbers, that information into y minus y1 equals m times x minus x1, and we solve it for y ultimately. So y minus y1 is y minus 1/4 equals m, which is negative 1/16 times, parentheses, x minus x1, which is x minus 4. Clean it up. Distributing the negative 1/16 will give us y minus 1/4 equals negative 1/16 x. Negative 1/16 times negative 4 is negative 4 over 1. The 4 and the 16 would reduce to a 1 and a 4. The negatives would cancel to positives, and you end up with positive 1/4. You better know how to clean up your fractions. So that's a plus 1/4. So y minus 1/4 equals negative 1/16 x plus 1/4. The 1 in the top, you could just write that as x over 16 as well. If you then add 1/4 to both sides, you better know how to add your fractions as well. No excuses. We get y equals, let me just write it over here, negative 1/16 x plus 2/4, which is negative 1/16 x plus 1/2. And that is our tangent line, but only at x equals 4. If you want to do it at x equals 3, you got to plug 3 into the function, which would be 1/3, plug it into the derivative, which would be negative 1/9, and then do the same equation. I don't ever have equations of tangent lines for a function that's a line because it's literally the line. This process is only done for curves. Things like x squared, x cubed, 1 over x, in theory, square root of x. But like I said, we'll focus on that idea later with a simpler equation. So that is where we're going to leave today at. I believe we have finished 1.3 and 1.4. There's just a couple very, very basic ideas that we need to discuss. Yeah, we'll say 1.4 is almost finished. We'll spend maybe 10 minutes doing one more example using the limit definition, and it'll be with a multiple term polynomial. I'll even say it out loud. It'll be x squared minus 5x plus 12. That'll be the first thing we do next class. Then we'll give you an alternate notation to the f prime of x, and then we'll talk about what it means to be differentiable and how some functions aren't differentiable at certain points, but they are at other points. So we did finish 1.3, so that means 1.3 is due in a week. So 1.3 is due, what's that, the 2nd? 1.4 will be due on the 4th? Yeah. So I'll put those in my math lab sooner than later. So I hope we all understood what I was talking about today as much as you could without practice. Go and do the homework to practice. Like I said, some of the homeworks in 1.3 are a little above our pay grade, so I'm gonna just kind of give you a free check on some of those. They do a lot more problems with the H values than I really think is necessary, since I don't emphasize that really at all moving forward, except maybe one more time later in the semester. So in terms of testing, I'm much more interested in problems like, oh, wrong thing, and like what we were doing here and here and here. This is test stuff. The homework is just a little above and beyond every now and then. So with that being said, if you have any questions, please email me. If you have any questions in the next 10 seconds, you can go ahead and ask, but please email me. Like I said, I check the Canvas email, but it doesn't always tell me I have messages. So if I don't get back to you within 24 hours, just send me a regular email. Hey, Mr. Beckner, what's going on? Yeah, so have a good one. We'll see you Thursday. Ready to finish 1.4 and then get into 1.5. Take it easy and work hard, study hard.